Have you ever noticed how some apps just seem to know what's happening the very second it happens?
Yeah, like a live sports score that updates instantly, or a news alert that pops up right as the news breaks.
Right. There's some pretty impressive technology at play to make all that real-time magic work, and today we're diving deep into one of those fascinating tools, server-sent events.
SSE for short.
Exactly. Think of this deep dive as your crash course on how servers can push updates to your device in real time.
And whether you've bumped into SSE before, or it's a totally new concept for you, our aim today is to walk away with a solid understanding of what SSE is all about, and, more importantly, when it's the right tool for the job. We've got some excellent resources to help us with that, including some very practical Python code examples using FastAPI and IOTTP. Plus, we'll compare and contrast SSE with other real-time technologies like WebSockets and even the old-school method of polling.
So by the end of this conversation, you'll not only grasp the basics of SSE, you'll understand its strengths and recognize situations where it really shines. Whether you're a developer actively searching for solutions or just someone who's fascinated by how the internet keeps us so instantly informed.
We'll even sprinkle in some real-world examples you encounter every day, like those live dashboards and instant notifications to really bring it home.
All right, let's break it down. What exactly are server-sent events?
Okay, so picture this. Your web browser needs to know when something changes on a server. With traditional web requests, your browser has to constantly ask the server, hey, anything new? Hey, anything new? It's like constantly checking your mailbox, hoping for a letter.
It sounds exhausting.
It is, and that's where SSE comes in. SSE flips the script. Imagine your server has a megaphone, and it can directly broadcast updates to your browser. No more asking repeatedly. This simplicity, the server just pushing information, that's the heart of server-sent events.
So the server just shouts it out whenever something changes.
Exactly. And crucially, it's a one-way communication street. The server talks, and the client listens.
One-way street. Got it. So not a back and forth conversation. And the sources mention this all happens over HTTP streaming. What does that mean?
Right. So typically when you load a website, the server sends you one big chunk of information and then says, okay, I'm done, and closes the connection. But with SSE, things work differently. It takes advantage of a feature in HTTP called streaming. This keeps the connection between your browser and the server open. It's like a dedicated pipeline where the server can continuously send new data as soon as it has something to share.
So a constant open line where the server just keeps the updates flowing. I'm starting to get the picture. So when is this one-way server-to-client system actually useful in the real world?
You know those live dashboards that show things like website analytics or sensor readings from a device, or even those live sports scores we talked about? Those are great examples. The server knows when those numbers change, and it needs to instantly push those updates to everyone who's watching. Real-time notifications are another perfect use case. Think about it. When you get an alert for a new email or a social media update, the server is the one initiating that push to your device, often using technologies like SSE.
Ah, okay, I see. So if I'm mostly just displaying information that the server is updating constantly, SSE sounds like a really streamlined way to handle that.
Absolutely. And even streaming data like stock prices or news feeds fits perfectly into this model. The server has this continuous flow of information, and it just broadcasts it out to any interested clients.
What if my application needs to send data back to the server frequently? Like if it's more of a two-way conversation in real time?
That's a really important distinction. If you need that constant back and forth flow of information where both the client and the server are actively sending and receiving data, think about a chat application or an online multiplayer game. In those cases, SSE isn't the best choice.
What should you use in those cases?
The sources actually point to WebSockets as the more suitable technology for that. WebSockets enable that full duplex communication, that constant two-way street, which is crucial for those super interactive experiences.
Okay, so SSE is for when the server is doing most of the talking, and WebSockets are for when it's more like a real-time conversation.
Got it. Now, our sources included some actual Python code examples, which is fantastic.
Yeah.
Let's start by looking at how to set up a basic SSE server using FastAPI. Where do we even begin?
Well, like with any Python project, the first step is to make sure you have all the necessary tools in your toolbox.
Of course.
The tutorial mentions a few key packages that you can easily install using pip.
Pip install.
Right. You'll need FastAPI, which is a really nice modern web framework.
Yeah.
Think of it as the foundation of our server.
Okay.
Then there's Unicorn, which is like the engine that takes our FastAPI code and turns it into a running web server.
Okay, so FastAPI and Unicorn. anything else.
And while we'll mainly use EUTTP later on for the client side, it's also helpful to have that installed as well.
So a quick pippins, Verstappen, Uvicorn, AUTTP in the terminal, and we're good to go. What's next in the server code? All right, so now we get to define our fast API application. And the real star of the show here is this function called event stream. This is a special type of Python function called an asynchronous generator.
Okay. And what's so special about that?
It's designed to produce a stream of events continuously.
I
In this
see.
simple example, it's just simulating sending a new event every 2 seconds. It uses a counter that goes up with each event, and then it formats a message in a specific way. It looks like this: data, message counter GAND.
Interesting.
That data, followed by the actual message, and then those 2 blank lines, that double new line, that's the standard way of signaling a server-sent event.
So it's like the server is saying, hey, client, new SSE message here.
Exactly. It's like a neatly labeled envelope that the server sends, making sure the client knows exactly what kind of information it's getting and where one message ends and the next one begins.
Clever. What about that 2-second pause between messages? How is that handled in the code?
Oh, that's taken care of by this line, await asyncio.sleep2. It basically introduces a 2-second delay between each simulated event, mimicking how a real-time data source might update periodically.
Okay, that makes sense. So we've got this event stream function generating these messages every 2 seconds. How do we actually make these events accessible to clients?
Right. We need to give our Fast API application a specific address or an endpoint where clients can connect to receive this stream of events. In this case, it's SSE.
So if a client visits SSE, they'll start getting this continuous flow of messages. How does that work in the code?
We use Fast API streaming response.
Yeah.
We hand it our event stream generator function. And importantly, we set the media type to text event stream.
What does that do?
That's the signal. It tells the client, whether it's a web browser or a dedicated program, hey, this isn't a regular web page. It's a continuous stream of events formatted in the specific way that you can understand.
Got it. So when I point my browser or a client to Fast API with Uvicorn doing its thing under the hood, starts running that event stream function, and it just keeps that connection open, sending out those formatted messages every 2 seconds.
Exactly. And the tutorial even walks you through how to get this server up and running. You save your code as a Python file like sserver.py, and then in your terminal, you simply run python sserver.py.
And what happens then?
You should see a message indicating that Uvicorn is running typically on a specific address like http://0.0.8000000. That means your SSE server is live and ready to start broadcasting those events.
Fantastic. So the server's all set up and sending out these messages, but how does a client actually tune in and listen to the stream of events? Our source provides an example of a Python client using that AOTTP library we installed earlier.
Right. So on the client side, we'll also need to import the necessary libraries. We'll use AOTTP for making those asynchronous HTTP requests and asyncio for running our client function. The main logic is within this function called sclient.
Yeah.
And it's defined as async, which is important. First, we need to specify the address of our SSE endpoint on the server, which is http://localhost.8000ac in this case.
Okay.
Then we use a HTTP client session to create an HTTP client session. Imagine this is getting your browser ready to make a request.
Makes sense.
And then within this session, we open a GT request to our SSE endpoint using session.getURL.
Okay, so we're essentially connecting to that SA endpoint. Now what?
Now, here comes the cool part. We use this loop, async for line in response.content. This loop goes through the content of the HTTP response line by line.
Okay.
Because it's an SSE stream, the response.content will keep yielding new lines of data as the server sends them. So the client is basically listening to that open pipeline, waiting for whatever the server pushes through.
So as the server sends those data messages through the open connection, the client's AOTTP connection is picking them up and making each line available within this loop.
Exactly. And inside the loop, the code first checks if we've received a complete line of data.
And if it has.
Then it decodes that line from its raw format and prints it to the console so you can see the message received from the server.
All right, so the client is displaying the server's messages. How do we actually run this client code?
Easy. We just need to save our code as another Python file, maybe sclient.py, and then in a separate terminal window, we run python sclient.py.
And if everything's working correctly, we should start seeing output like received from server.data, message 1, followed by received from server.data, message 2, and so on. Each message neatly displayed as the server diligently sends those updates every couple of seconds.
Precisely. And what's really important to grasp here is that the client doesn't need to keep asking the server for updates. That initial connection is all it takes. From then on, the server takes the lead and pushes data as soon as it becomes available.
It sounds much more efficient than having the client constantly bugging the server for updates.
It is. And this efficiency is a big reason why choosing the right technology for real-time applications is crucial. Speaking of which, our sources show us another neat trick. You can even use a simple command line tool like curl as a basic client to listen for these SSE events.
Wait, really? Curl can do that?
Yeah, it's surprisingly straightforward. The command is curl-nhh except text ad-stream http://localhost.8000 access.
Okay, let's break that down.
Sure. The AD flag tells curl not to buffer the output it receives. Basically, it says, show me the data as it arrives. Don't wait for the whole thing.
Got it.
Then there's the ADH except text event stream part, which is really important. It sends a specific HTTP header to the server.
What does that header do?
It's like the client introducing itself, saying, hey, server, I'm here, and I'm expecting a stream of server-send events. And finally, we have the address of our SSE endpoint.
So when you run this command curl, connects to the server, sends that header announcing that it wants an event stream, and then the server starts piping those data messages directly to your terminal.
Precisely. And in your terminal, you'll see the raw, unformatted SSE output, data.
Yeah.
Message 1, then data, message 2, and so on. It's a handy way to quickly check if your server is sending the SSE stream correctly without even needing a full-blown client application.
Okay, so we've seen how SSE works with a Python server and client, and even the super basic curl client. That's awesome. Our sources also give us a really helpful comparison of SSE with its main alternatives, WebSockets and polling.
That comparison table is really illuminating. It helps you decide when you might choose one technology over the others.
Let's dive into that table then.
Let's start with connection type. As we've discussed, SSE is one way from server to client.
Right.
WebSockets, on the other hand, offer a two-way or full duplex connection, meaning both the client and the server can send and receive data at any time. And then we have polling, which is a totally different approach.
Yes.
Polling doesn't maintain a persistent connection at all. The client keeps asking the server, hey, anything new? Hey, anything new? At regular intervals.
It's like that annoying kid in the back seat on a road trip. Are we there yet? Are we there yet?
Exactly.
And in terms of what they're primarily used for, the table really reinforces what we've already talked about. SSE is best for those live updates and notifications where the server is the main broadcaster.
Right. WebSockets are the go-to for interactive things like chat and online games, where you need that constant back and forth. And polling seems to be more for basic updates where real-time responsiveness isn't absolutely critical.
Exactly. So what about efficiency? How do they compare in that department?
Well, because SSE uses that single long-lived HTTP connection, it's generally very efficient for server-to-client updates. WebSockets are also efficient because of that persistent connection, but for two-way communication. Polling, however, tends to be quite inefficient. The client is always sending requests, even if there's nothing new on the server. And that can put a lot of strain on both the client and the server. Plus, it introduces delays because you only get updates when the client happens to ask.
I can see how that would be a problem. And what about browser support?
That's another important consideration. SSE is natively supported in most modern web browsers, which is a huge plus.
So you can often just use it directly with JavaScript.
Exactly. WebSockets also have pretty good browser support, but they usually require a specific JavaScript API to set up and manage that connection. And polling, well, it just uses standard HTTP requests, so it's the simplest in terms of browser support. But like we said, it's not ideal for real-time applications because of those efficiency and speed issues.
So the key takeaway here seems to be that if you need the server to push real-time updates to the client and you don't need a lot of back and forth, SSE is the way to go.
Exactly. And WebSockets are there for when you do need that two-way street. And polling, well, it's generally something you'd want to avoid for true real-time applications because of how inefficient it can be.
Our tutorial actually goes beyond just explaining SSE. It also shows how you can integrate it with other tools like Docker and Streamlit to build a more complete real-time application.
Right. It takes the basic SSE server we just talked about and packages it up neatly in a Docker container.
A Docker container?
It's like putting all the pieces of your application in a little box that can run anywhere.
Ah, okay.
And they also create a separate client and a web-based front end using Streamlit.
What's Streamlit?
It's a really cool Python library that makes it ridiculously easy to build interactive web applications, especially for data-related stuff.
So in this expanded example, they have 3 different services, all defined in this docker-compose.eml file. One for the SSE server, which is our fast-to-PI app. Another for a dedicated SES client, which is that PyCon listener we looked at earlier. And then a third for the front end, which is the Streamlit app. Okay, I'm following so far.
Now, what's particularly interesting is that the Streamlit front end actually uses the request library to connect to the SSE server and then displays those incoming messages live in a user-friendly web interface.
Oh, that's neat. So instead of just seeing raw messages in a terminal, you get to see them updating in real time in a web browser.
Exactly. It makes the whole concept much more tangible and shows how SSE can be a part of a real-world user-facing application.
That's really cool. So the tutorial walks you through how to set all of this up using Docker, and then you can actually see those messages appearing live in your web browser.
And then the tutorial goes a step further and introduces a more interactive scenario where the client can actually send messages back to the server using that Streamlit interface and receive acknowledgments through the SSE stream.
Wait, so we can get some kind of two-way communication going even though SSE is inherently one way? How does that work?
It's pretty clever. They add a new endpoint on the server side at messages.
And what does this endpoint do?
This endpoint is specifically designed to receive messages that are sent using the PST method, usually containing data in JSON format.
Okay.
Now, when the server receives a message at this messages endpoint, it doesn't just send back a regular immediate response like you'd expect with a typical API.
What does it do instead?
It uses this thing called an Asensio queue. Think of it as a little message holding area within the server.
Okay.
When a new message comes in via messages, the server processes it and then puts a confirmation message onto this queue.
I see. So how does this confirmation actually get back to the client through the SSE stream?
Well, the existing SSO endpoint, the one that's running our event stream function, is updated. Now, instead of just sending out a counter every 2 seconds, it also checks if there's anything waiting in that message queue.
Oh, okay.
So whenever a new message is added to the queue, whether it's from that initial counter example or from a new message arriving at messages without him, the event stream function grabs it and sends it out to all connected clients in that standard SSE format.
So the server is kind of piggybacking on the existing SSE connection to send these confirmations back to the client.
Exactly. It's a neat way to simulate a form of two-way interaction, or at least give some feedback to the client, even though SSE is fundamentally a one-way push from the server.
So on the client side, the Streamlit frontend is updated to include a text input field and a send button.
Right. So you can type in a message, hit send, and the Streamlit app will make a post request to the messages endpoint on the server, including your message in JSON format.
And then?
The server receives the message, puts an acknowledgement on the queue, and then all connected SSE clients, including the one that just sent the message, will receive that acknowledgement as part of their continuous SSE stream. And the Streamlit app will display it neatly in an incoming messages section.
So while the initial SSE connection at SSE is still primarily a server-to-client push cage, this setup cleverly uses that same stream to send back confirmations of actions initiated by the client through a separate channel, the messages endpoint.
It's a really elegant way to achieve a form of two-way communication within the constraints of SSE.
It sounds like a powerful pattern for building those modern web applications that need to be interactive and provide real-time updates at the same time.
It is. And speaking of different approaches, our sources highlight another important comparison: the difference between SSE and traditional REST APIs.
REST API.
Yes. It's worth understanding how these two approaches differ. The fundamental difference lies in how the communication is initiated. REST, which stands for Representational State Transfer, follows a request-response pattern.
Okay.
A client sends a request to the server, and the server processes the request and sends back a response, and then the connection is usually closed. SSE, as we know, is different. It's the server that initiates the communication, sending data to the client over a persistent open connection.
So REST is more like a quick exchange of information, and SSE is like a continuous flow.
Exactly.
So when would you typically use REST versus SSE?
REST is your go-to solution for actions like fetching information about a user submitting a form or generally working with data.
What about SSE?
SSE shines in those real-time scenarios we keep talking about. Things like delivering notifications, providing continuous updates for things like stock quotes or sensor data streaming news feeds. Any situation where the server needs to tell the client about new information without the client having to constantly ask.
And we already talked about how they differ in terms of connection type. REST uses short-lived connections, while SSE uses a persistent connection. What are the implications of that for efficiency?
Well, REST relies on the client making those repeated requests to get the latest data, which can introduce delays, especially if the client needs frequent updates. Each quest has its own overhead. SSE, with its persistent connection, allows for low latency updates because the server can push data whenever it's ready. However, it's worth noting that maintaining lots of open connections can also have an impact on the server's resources.
I see, so there are trade-offs to consider. Our tutorial gives a clear example of a REST interaction. A simple get users 123 request that might return a user's details as a one-time response. And for SSE, it uses the familiar getS endpoint that gives us that continuous stream of data messages.
Right. And the sources even include a really useful table that summarizes when to use REST versus SSE based on different scenarios. Like if you need to fetch some data once or submit a form, REST is the clear choice. But if you need live notifications or continuous data streams, SSE is generally the better fit.
Makes sense. And we know that for truly two-way interactions like a chat application, WebSockets would be the more appropriate technology.
Absolutely. Now, the tutorial actually goes a step further and demonstrates how you can combine REST and SSE within the same application. They introduce a new REST API endpoint at SendREST.
Oh, interesting. What's the idea behind that?
This endpoint allows clients to send messages to the server using a regular REST API call. This can be helpful for clients that aren't primarily set up to consume an SSE stream or for actions that naturally fit that request response model.
Okay.
But here's the cool part. When the server receives a message at SendREST, it doesn't just send back a standard REST response. It also takes that same message and puts it on that message queue that feeds our SSE stream.
So you can interact with the server using a regular REST API call and get that immediate confirmation that your action was successful. But that same action also triggers a real-time update to any other clients that are connected to the SSE stream.
It's like getting the best of both worlds. The reliability and immediate feedback of REST for specific actions, combined with the real-time broadcast power of SSE for wider updates.
So they essentially bridge the gap between these two paradigms, REST and SSE, allowing you to leverage the strengths of both.
Exactly. The Streamlit front end in the example is even updated with a second button, Send as REST. When you click that button, the app sends a standard post request to send REST with your message. You get back a typical HTTP response confirming the server received it. But behind the scenes, that same message is also being added to the SSE queue, so an event is generated and sent out to all connected clients.
So it appears in their incoming messages section.
Precisely.
Wow, this has been a super informative deep dive into server-sent events.
It has.
We learned that SSE is a great way to push real-time updates from a server to clients over a persistent HTTP connection. It's perfect for applications like live dashboards, notifications, streaming data.
And we went through the process of building a basic SSE server and client using Python and FastAPI and AOTTP.
We even saw how to use curl to check out an SSE stream.
And of course, we talked about how SSE compares to WebSockets, which are better for two-way communication, and polling, which is generally less efficient for real-time needs.
And to top it off, we learned how to cleverly integrate SSE with those traditional REST APIs so you can have both immediate responses and real-time broadcasts in the same application.
It's all about choosing the right tool for the job.
Exactly. So as you're thinking about how to add real-time features to your own projects, keep in mind the direction of that data flow.
If you mainly need the server to broadcast information to lots of clients, and those clients don't need to send a lot of data back in real time, SSE is a very streamlined and efficient solution.
Definitely more efficient than using something heavier like WebSockets for those scenarios.
So whether you're building the next amazing live data dashboard or just curious about how those instant updates work, remember server-sent events.
It's a really powerful tool to have in your web development arsenal.
And if you want to explore SSE even further or need some personalized guidance, the team at https://www.sogini.com offers one-on-one training and consulting. They can help you master these concepts and apply them effectively.
That's an amazing resource for anyone who wants to take their understanding to the next level. Well, that wraps up our depth dive into server-sent events. Thanks for joining us today.
And we'll see you in our next exploration.